Good morning, friends. Already we discussed about the numerical of illustration, and also in exercise up to the 10.15 numerical also we discussed with the theory. Now today we are going to start our discussion about the numerical of exercise from 10.16. Now 10.16 is depends on the equation of continuity. Now what is given? A cylindrical tube of spare pump has the cross section of 8 centimeters square at one end, while at the other end, which has the 40 fine holes, each of diameter 1 millimeter. If the liquid flow inside the tube is 1.5 meter per minute, what is the speed of ejection of the liquid through the holes? Now this numerical is like this way. One tube is given. One end of a tube having the diameter is given. Here the cross section area given the A1, and whatever the fluid is flowing, having the speed is V1. While at the other end, here the 40 holes are given, small holes. Each hole has the diameter is given 1 millimeter. We have to find out the fluid coming out of this hole. What is the speed of the fluid coming out from the hole? For that purpose, first we have done the given data. Cross section area of one end of a pipe. Cross section area of one end of a pipe or the tube that is given is A1. A1 is given as the 8 centimeters square. Convert into meter, 8 into 10 raised to minus. Here 8 centimeters square, 8 into 10 raised to minus 4 meters square. Right. Now, also the speed of fluid V1 is given in form of meter per minute, 1.5 meter per minute, convert into meter per second. Therefore, 1.5 divided by 60 meter per second. So it's equal to 0.025 meter per second. Right? Okay. Now at other end, diameter of a hole D is given the 1 millimeter. Therefore, radius of the hole R is equal to D by 2, that means the 0.5 millimeter. Therefore, area of each hole, small a is equal to pi r square. So it's equal to pi, r is 0.05 into 10 raised to minus 3 whole square. Right? That is the cross section area of each hole. So it's equal to 25 pi into 10 raised to minus 8 meters square. Check it. Now, number of holes is equal to 40. Therefore, cross section area at other end A2 is equal to 40A. Therefore, 40 into 25 into pi into 10 raised to minus 8 meters square. That is the value of small a. Now, 25 is 100 into this 0, that means the 1000. Therefore, 1000 pi into 10 raised to minus 8 meters square. Pi is 3.14. 1000, that means the 10 raised to 3. Here 10 raised to minus 8. Therefore 10 raised to minus 5 meters square. That is the A2. We have to find out the V2. Right? Therefore, how we find out the V2? That means the speed of the ejection of the fluid from the holes. For that purpose, from equation of continuity, A1 V1 is equal to A2 V2. Therefore, V2 is equal to A1 V1 upon A2. A1 already we know. 8 into 10 raised to minus 4 into V1. V1 is equal to 0.025. 0.025 upon A2. 3.14 into 10 raised to minus 5. If we simplify, we get the answer is 0.64 meter per second. That is our answer of the speed of a fluid coming out from the each hole. Only the application of the equation of continuity. But first we have to attempt what are the details given. Our concept must be clear about that. What is given? The pipe is given. One end of the pipe having the cross-sectional area is A1. A1 is 8 centimeters square. Convert into meters square. Therefore, 8 into 10 is to minus 4 meters square. The speed of the fluid flowing through the tube is given. V1 is 1.5 meter per minute. Convert into meter per second. Therefore, 1.5 divided by 60 meter per second. Simplification is 0.025. Right? That is the meter per second. Now at other end, 40 holes are given. Each hole has the diameter is 1 millimeter. Therefore, the diameter of each hole, D, is 1 millimeter. Therefore, the radius of each hole, I is equal to D by 2 is equal to 0.5 millimeter. Therefore, area of each hole A is equal to pi r square. Pi as it is, the square of the radius 0.5 millimeter, that means 0.05 convert into meter, 10 raised to minus 3 whole square. Therefore, 25 pi into 10 raised to minus 8 meter square. Now the number of holes are given 40. Therefore, the cross section area at the end A2 is equal to 40 times of the area of one hole. Now, 40 as it is, value of small a is 25 pi into 10 raised to minus 8 meters square. 25 holes are 100 and this 10, therefore 1000 pi 10 raised to minus 8 meters square. 1000, that means the 10 raised to minus 10 raised to plus 3, 10 raised to plus 3, 10 raised to minus 8, 10 raised to minus 5. Pi 3.14. Therefore, the cross-sectional area at other end is 3.14 into 10 raised to minus 5 meters square. We have to find out the speed of a fluid coming out from the hole. We have to find out. Therefore, we are applying the equation of continuity. A1 V1 is equal to A2 V2. Therefore, V2 is equal to A1 V1 upon A2. A1 is our 8 into 10 raised to minus 4. V1 is this 0.025. And A2, just we find out 3.14 into 10 raised to minus 5. As we simplify, we obtain the answer is 0.64 meter per second. Clear is? Okay. After that, the next numerical 10.17, U-shaped wire is dipped in a soft solution and above. That means here we have the U-shaped wire. The one wire can move without the friction on both arms. This U-shaped wire is dipped in a solution and taken out. So what's happened? A thin soft film is formed between the wire and slider. That is the slider having the length is N. So this type of the thin film of a soft solution is formed. Now we know that due to the surface tension, the wire is lying in this side. Therefore, in equilibrium position, we have to apply the some force F against the surface tension. Okay, is formed between the wire and slider, supports a weight of 1.5 to 10 raised to minus 2 Newton. Here the weight, that means the force is given, F is equal to W. The length of the slider is given 30 centimeter. What is the surface tension of the fluid? The length of the wire L is given 30 centimeter. That means the 30 into 10 raised to minus 2 meter. Right? The force acting on a wire, F is equal to 1.5 to 10 raised to minus 2 Newton. Now our definition of the surface tension. The force acting by unit length of the wire and also perpendicular to the wire and parallel to the surface, that is known as the surface tension. Therefore, F is equal, surface tension S is equal to F upon 2F. Here surface has two phase surface. Therefore, we take the 2 in denominator. Therefore, F upon 2L. So it's equal to 1.5 into 10 raised to minus 2 upon 2 into length L. L is given 30 into 10 raised to minus 2. So the simplification of this is 2.5 into 10 raised to minus 2 Newton per meter. That is the surface tension of the soft solution. Again, only the application of the definition of the surface tension. The force per unit length of the wire perpendicular to the wire and parallel to the surface. S is equal to F upon 2. We are applying this equation to obtain the answer of this debate. Clear? Okay. Now 10.18 is cancelled. Now 10.19. But instead of the 10.19, first we take the 10.20. Okay. What is given? What is the excess pressure in a bubble of soap solution of radius 5 millimeter? Right. Surface tension of a soap solution is 2.5 to 10 raised to minus 2 Newton per meter. If an air bubble of the same diameter is formed at depth of 40 centimeter inside a soap solution, what should be the inside pressure of a bubble? So we need to find out the excess pressure of an air bubble formed by the soap solution in a medium, and next we have to find out again the pressure difference in case of a soap solution, air bubble formed inside the soap solution. And then we have to find out what is the inside pressure of the air bubble inside the solution. Right? Okay. For that purpose, here the radius of an air bubble. The radius of a bubble R is given as what is 5 millimeter. That means the 5 into 10 is to minus 3 meter. Right? Now surface tension S is given as 2.5 to 10 is to minus 2 Newton per meter. So first we find out the excess pressure in a bubble. Right? Therefore, excess pressure of a bubble so we can write the Pi minus Pu is equal to force upon R. That is in a medium. That is in a medium. substitute the value 4. S is 2.5, 10 is 2 minus 2 upon radius 5 into 10 is 2 minus 3. So it's equal to 20 Pascal or the 20 Newton per meter. 20 Newton per meter. Now, the same air bubble is formed inside the soap solution at depth 40 centimeter. Inside a soap solution, depth H is equal to 40 centimeter. That means the 40 into 10 is to minus 3 meter. We need to find out the pressure inside the air bubble at depth 40 centimeter. For that purpose, the axis pressure in a bubble in soap solution is Pi minus Po is equal to 2S upon R. Already we find out the 4S upon R, that is the 2S upon R, half of this. Therefore, directly I can add the 10 Newton per meter, or the 10 Pascal. 10 Pascal directly we can get. Now, the inside pressure in a bubble at depth H. Therefore, Pi is equal to Po plus 2S upon R. But Po is equal to atmospheric pressure plus each column of fluid produce the pressure is equal to H rho G. Therefore, instead of the Po, we can add the Pa plus H rho G plus 2S upon R. Pa is given 1.01 into 10 is to 5. H 40 centimeter, 40 into 10 is to minus 2. Relative density of a soap solution is given 1.2 into 10 is to 3. G 9.8 2S upon R 10. It is simplified, we obtain the answer is 1.06 into 10 is to 5 Pascal or the Newton per meter. That is our answer. Clear? So this type of the numerical may be asked in exam for 3 marks. First, read the question carefully. So first here, the air bubble of soap solution is formed in a medium. We have to find out the axis pressure. Therefore, Pi minus Po is equal to 4S upon R. Here the bubble is formed in a medium. It has the 2 free surfaces. Due to that reason, here the pressure difference is 4S upon R. Now we substitute the value of S and R in this equation. So it's equal to 4. Surface tension of a soap solution is given 2.5 into 10 is to minus 2. Upon radius is 5 millimeter. So convert into meter, 5 into 10 is to minus 3. Therefore, the 20 Newton per meter is the axis pressure in air bubble in a medium. Now, the same air bubble of same diameter is formed at depth 40 centimeter in a soap solution. So inside a soap solution, depth is given H is equal to 40 centimeter. Therefore, 40 into 10 is to minus 2 meter. Therefore, the axis pressure in bubble inside a solution, inside a soap solution is Pi minus Po is equal to 2S upon R. Already we calculate the 4S upon R, here the 2S upon R, that is the half of this. Therefore, directly we can add the 10 Newton meter. Now, what is the inside pressure of an air bubble inside the soap solution? Therefore, inside pressure in a bubble at depth H, Pi minus Po is equal to 2S upon R. Therefore, Pi is equal to Po plus 2S upon R. But at H depth, what is the outside pressure? Outside pressure is the addition of the atmospheric pressure plus the pressure due to each column of fluid. Therefore, PA plus A0G plus 2S upon R. We substitute the value, we obtain the final answer is 1.06 into 10 is to 5 Pascal or the Newton per meter. Clear? Okay. Now the next numerical of exercise 10.19. That is given as what is the pressure inside the drop of mercury of radius 3 mm at room temperature. Room temperature we consider at the 20 degrees centigrade because the surface tension of the mercury at 20 degrees centigrade is given 4.65 to 10 is to minus 1 Newton per meter. The atmospheric pressure is also given 1.01 into 10 is to 5 Pascal, and also obtain the excess pressure inside the drop. Now here the drop is formed in a medium and drop has the one free surface. Therefore the pressure difference between the inside and outside surfaces of a drop is Pi minus Pu is equal to 2S upon R. Right? So first we write down the data given. The radius of a drop small r is given as 3 millimeter. Convert into meter, 3 into 10 is to minus 3 meter. 3 into 10 is to minus 3 meter. Surface tension of mercury S is given as 4.65 into 10 is to minus 5 minus 1 Newton per meter. Atmospheric pressure PE is given as the 1.01 into 10 is to 5 Pascal or the Newton per meter. Now listen, here the drop of mercury is formed in a medium. So here the mercury, here the air medium. So outside pressure is PO, inside pressure is PI. Drop has the one free surface. Drop has one free surface. Therefore, the pressure difference Pi minus Pu is equal to 2S upon R. Now we substitute the value 2. S is 4.65 into 10 is to minus 1 upon. Radius of the drop is 3 millimeter. That means the 3 into 10 is to minus 3. Now we simplify it. So we obtain 310 Pascal or the Newton per meter. That is the pressure difference in case of a drop of mercury. Now next we have to find out the inside pressure of or the excess pressure inside the drop. Inside pressure of a drop. There is the Pi. Pi is equal to PO plus 2S upon R. But drop is in a medium. So PO is equal to PA. Outside pressure is only the atmospheric pressure. Therefore, PI is equal to PA plus 2S upon R. 2S upon R already we obtained. That is the 310. Therefore, we substitute the PA. PA is 1.01 into 10⁵ plus 2S upon R already we obtained. That is the 310. Therefore, 1.01 310 into 10⁵ Pascal or the Newton per meter. That is our answer. Or in other words, we can also add 1.01 into 10⁵ Pascal. That is the inside pressure of the air bubble. Why the both are same? Because in this situation the drop is in equilibrium. Therefore, inside pressure and outside pressure are equal. Outside pressure is the atmospheric pressure. Outside pressure is atmospheric pressure P. Therefore, inside pressure is also same as the atmospheric pressure 1.01 into 10⁵ Pascal. Clear? So first here we find out the axis pressure and then we calculate the inside pressure of the drop. Here the drop of mercury is in air medium, there is an equilibrium, therefore the both pressure are equal inside and outside. Outside pressure is equal to the atmospheric pressure, therefore PI is also the same as the atmospheric pressure 1.01 into 10⁵ Pascal. So here the numerical of exercise are also completed, right?